Gradient of KL divergence. In the last lecture, we learned about KL divergence. We understood what exactly is the concept of KL divergence, what is the idea behind it, what is the logic behind it, and then we understood what is the mathematical formulation for KL divergence, how this comes up, what is the idea behind that mathematical formulation, and then we also understood where to use it, what is the exact purpose. Here, we are going to see what is the gradient of KL divergence loss. One thing that I always tell you is that whenever you learn about a loss function in machine learning, it is very important that you know how to find the gradient. This is because if you have a model and you want to update the model parameters, what do? You pass your input through the model, you get the output, then you have to calculate loss, then you are going to back propagate this loss. While you are back propagating the loss, how do you decide how much should you modify each of the model parameters? This modification is done based on the gradient. So you should know what is the gradient in order to know to what extent you should modify each parameter in this particular round of backpropagation. So let us say you are using gradient descent or something for optimization as an optimization algorithm. That is where gradient comes handy. Let us see how to find out the gradient of KL divergence. In the last lecture, we learned about KL divergence loss. So the formula can be written as KL divergence of Q from P. This can be written as summation over all the K classes. Let us say K is the total number of classes and you have two distributions. One is P, which is the true distribution. Q is the distribution that is output by the model. The predicted distribution by the model is what you're calling as Q. P is the true distribution, right? Then here, summation over all the classes, K equal to 1 to K. What do you want to do? Pk log Pk by Qk. What are these small p's and small q's? Small p, this is the true label. Let us say you have actual true distribution p. From that, for this particular example, here we are taking one example. In that example, what is the true label? That is what you are using the p vector. It will have p1, p2 up to pk. This will tell you what is the true label. And what about q? Q is what is predicted by the model. This is the predicted label. Okay. So this comes from distribution Q, which is built by the model. Q is the predicted distribution by the model. Okay. So this is the setup. What do you want to do now? You want to find the gradient. That is, you want to take derivative of this loss with respect to the model output. Let us say your model output, you will call it as y cap. So in the previous lectures also you used cap for representing output. If one doubt you can have here is, I already told you that Q is what is produced by the model. That is predicted distribution by the model, that is Q, and I represent the label as small q. Then what is this y cap? This is the confusion you can have. And the answer is, your model is not going to directly produce probabilities. Instead, this will be raw logics as output. This output is what I am calling as y cap. This output would just be real number. You will apply softmax on this output. Softmax, when it is applied, you convert this y cap into probabilities, which I am calling as q cap. Okay. Or q. Here I didn't put cap, I just put q. So this y cap, when converted to probability using softmax, becomes q. So this is the logic. Okay. What we'll do, we'll see the complete derivation of KL divergence gradient. Instead of writing KL of all these, I'll simply write L because that will be easier. It is the loss. I'll write L. What do we want to do? We want to take del L by del yi cap. This is what we want to do. Del L by del yi cap. This is what we want to find out. With respect to each of the yi, That is, in y cap, you will have a vector like y1 cap, y2 cap, so on up to yk cap. With respect to each of these, you will have to find loss. This is with respect to each of these, you will have to take derivative of loss, which is the gradient, and this you will back propagate in order to improve your model. What you have to do here is, let us see how to take this derivative. If you want to take this derivative, first thing you want to understand which are the terms of significance here. There are some terms which we can remove from here. Let us see which are those. If I write this formula here, L is equal to, my loss is equal to summation overall k equal to 1 to k pk log pk by qk. If I expand this, what happens is this will become summation over all the k equal to 1 to k. One term will be pk log pk. I am going to split this. This will become pk log pk minus summation over all the terms from k equal to 1 to k pk log qk. So how did I get this? Log a by b can be written as log a minus log b. So this will become log pk minus log qk. Then I simply split it, okay? This can be written as log pk minus log qk. Once I write in this form, then if I multiply with this pk, it becomes pk into log pk minus pk into log qk. Now observe this very carefully. You are going to take the derivative with respect to yi cap, that is with respect to distribution q, not distribution p. But this term, this is a constant with respect to q. You think with respect to q, there are no terms related to q at all here. This is all coming from distribution p, purely from p, which means when you are going to take derivative with respect to q, then this one will be constant. So with respect to q, this term is a constant, which means when we are taking the gradient, this is not significant. So you can remove this part, even though that is part of loss. When you are taking derivative, it is not significant. So actually we want to take derivative of this only, because other one is anyway going to be 0. So this is the term of significance. I'll write it here. This can be written as, instead of this, I'll put this sign, because actually it is not equal to this. I'm saying when taking derivative, the other term is not significant. So you need to consider only this. K equal to 1 to k pk into log qk. So this is your term. Let us see how to take derivative of this and find out what is the gradient of KL divergence. Okay. So first thing, you have a softmax. What is your qk? Your qk is expressed as e power yk cap divided by sum over all the terms j equal to 1 to k e power yj cap. So this you will already be familiar from the previous lectures, that softmax of y cap is what you are calling as q. So softmax of yk cap is what you are calling as qk. Next thing is, what we want to find is del L by del yi cap. This is what you want to find. If you do this with respect to this loss, what happens? It will become del L by del yi cap. This can be written as del by del yi cap of, as of now I am just copying the term, then we'll simplify, sigma k is equal to 1 to k pk log qk. So this time I just copied this term, okay, nothing else. Now we are going to simplify this. How can we simplify this term? If I simplify this, I can take this summation part, I can take this outside, because this part is not dependent on yi cap, because yi cap is only dependent on qk. What is yi? It is your model output, that is dependent on distribution q, which is produced by the model. And p is dependent on p, the distribution p, which means With respect to distribution Q, this part is a constant, so that won't have any role in this derivative. What I'll do is I'll take that part outside, minus sigma k is equal to 1 to k pk into, here I'll apply the del by del yi cap of log qk. This is where I am at. If I take this, I will understand what happens if I take derivative of log qk with respect to yi cap. Derivative of log x is 1 by x. So that will become 1 by qk. So this will be minus sigma k is equal to 1 to k pk by qk. How did this come? Because log qk when taken derivative becomes 1 by qk. Then I have to do del qk by del yi cap. This is the term that is remaining to be solved. This del qk by del yi cap. How can I solve this now? So at this point, I have to introduce to something here. Qk, this we already discussed, is the softmax. This is where I got it from. So one point is we can stop this derivative, this gradient here, because depending on qk, you have to find this out. So one idea is you can stop this here. But what I'll do is we can actually solve this to a better extent if we consider that your output, whatever is going to be the output of model, if that is going to be 1 hot, if you consider it as 1 hot, then you have a better option of solving this. So I'm going to consider that it is 1 hot and then we are going to solve it fully. So two things keep in mind. One is this is the gradient of KL divergence laws, that is sum over all the terms from k equal to 1 to k, that is through all the classes, pk by qk into del by del yi cap of qk. This is the gradient of KL divergence laws. I'm going to do a bit more of solving this in order to take it to a good form, a good looking form. But keep in mind that I'm considering after this point, whatever I'm doing, I'm going to consider that your model output, that is finally, sorry, not the model output, your true label. The true label that you have, that I'm going to consider that it is a 1 hot vector. Okay, that is the consideration I'm going to keep. So considering that it is a 1 hot vector, what will be this del qk by del yi cap? If you think about this, we had seen the same situation before. Few lectures back, you had a softmax, that is here qk is a softmax. You had a softmax and you had to take derivative of softmax with respect to yi cap. And there what did you do is you found out that del qk by del yi cap, this can be written as qk into del ik minus qi. So where did you find this? Few lectures back when we were learning about gradient of CCE, that is gradient of categorical cross entropy, we hit the same scenario. There, when we wanted to take derivative of the softmax with respect to yi cap, we found out that derivative is qk into del ik minus qi, where what is this delta? This del ik, this value, this will be 1 whenever I is equal to k, and del ik, this will be equal to 0 whenever I is not equal to k. See, I'm not solving this completely here because it will take up a lot of time, and we have done the exact derivation 2 lectures back. So if you want to see this derivation, how this came, please go back to the lecture on gradient of categorical cross entropy. In that lecture, we have shown exactly how this term comes up. So here I am going to directly use this thing, that derivative of softmax with respect to yi cap, it will come up as qk into del ik minus qi, where del ik will take value 1 whenever I equal to k, that is whenever it is the true class I equal to k. Ith class is same as the kth class you are considering here, and whenever del ik equal to 0, whenever I not equal to k, del ik will take value 0. This is the scenario. So I'm going to directly substitute here so that my solving will become easier. This is equal to minus sum over all the k equal to 1 to k, pk by qk into, what am I going to substitute here? This thing. That will be qk into del ik minus qi. So how can you solve this further? If I solve this further, this qk and this qk, they get cancelled. What remains? What remains is sigma k is equal to 1 to k pk into del ik minus qi. Now think very clearly, how am I going to solve this? Okay, we are going to take it into a very clear form. You had seen a very similar solution before, so it will be easier for you to follow. This will be minus sigma k is equal to 1 to k pk into del ik, and along with this minus and this minus, it will be plus the second term, plus sigma k is equal to 1 to k pk into qi. Now think very carefully about this. When will del ik take the value 1? Del ik will take the value 1 only when I equal to k, and it will be 0 in all other cases, which means in all the terms that are included in this summation, only one term will have del ik equal to 1. Only one term will have del ik equal to 1, which is when k equal to I. All other cases, del ik will be 0, which means this whole term will get cancelled out in all other cases. So in this summation, the left side, this part of summation, there will be k terms, out of which k minus 1 terms will be cancelled out because del ik will take value 0. Only one term remains, for which del ik will be 1 where I is equal to k. When I equal to k, pk is pi. So I can write minus pi. Okay, only one term remains from this summation. Plus, what is this term? If I write it as, see, qi is independent of this k. So I'll take qi outside, and then I'll write summation over all k equal to 1 to k pk. Do you know this term? Summation over all the classes, probability of k. We know p is a probability distribution. And what is the scenario here? If you sum all the probabilities, you will get 1. Sum over all the classes, k equal to 1 to k pk, this will be 1. Which means this term is cancelled out. It is 1. This only remains. So this can be written as qi minus pi. So this is the final form of the derivative that we have. This is the derivative of KL divergence. But keep in mind, I considered that it is a one-hot vector. If it is not considered, then depending on the situation, I may have to solve. This will be till this form, it holds everywhere. Then I used this formula, and it is similar to cross entropy. You can see the cross entropy lecture where there was one particular lecture which was specifically for finding the gradient of categorical cross entropy. If you refer to that lecture, you will understand this even more clearly. Moreover, you will be able to relate how categorical cross entropy is so closely related to KL divergence. Whenever you are learning concepts, if you understand how each concept is related to each other, it's much easier for you to learn. So that's why I specifically mentioned about that lecture. So you may try to correlate those. This is about the gradient of KL divergence.